Welcome back to The Explainer, Focused Learners. Today we are completely flipping the script on how we build artificial intelligence. We're talking about a massive paradigm shift here, a huge leap from systems that we painstakingly put together by hand to systems that actually build, repair, and evolve themselves. Let's dive right into a groundbreaking framework known as the Autogenesis protocol.
I want you to think about the absolute cutting edge of AI agents right now. They can browse the web, they can write code, they can even do your math homework for you. But I have a question for you. What happens when an AI encounters a problem it just wasn't programmed to solve? What happens when the environment shifts, or say a tool API breaks, or the instructions we gave it are just slightly too vague for some brand new edge case?
Well, usually it completely breaks down, right? It hallucinates, it gets stuck in an endless loop, or it just spits out a frustrating error. And right now, fixing that requires human engineers to jump in, dig through the code, and manually patch the prompt or the tool. But what if the AI didn't need us for that? What if it could literally rewrite its own instructions and tools on the fly? That is the exact promise of the Autogenesis protocol. To really demystify this incredibly dense framework, here's our roadmap for today. First, the brittle AI problem. Second, the missing link. Third, Layer 1, the substrate. Fourth, Layer 2, self-evolution. Fifth, testing the evolving agent. And finally, number 6, the new AI paradigm.
Section 1. The brittle AI problem. Why agents fail in the real world.
Let's start with the root of the issue. Why do today's AI agents fail so catastrophically in dynamic environments? The answer lies in how they're constructed. Most existing agent frameworks out there are what we call static and monolithic. Prompts, tools, memory. They're usually hard-coded right into the agent's core pipeline, held together by some pretty brittle glue code. It's kind of like welding the hood of a car shut. If something breaks in the engine, you can't easily get in there to fix it without tearing the whole thing apart. But Autogenesis proposes a shift to a self-evolving agent paradigm. We're talking dynamic, adaptable, and modular systems that actually adjust their own strategies and update their own tools based on immediate environmental feedback.
Section 2. The missing link. Why current protocols aren't enough. Now, you might be wondering, wait, don't we already have ways for agents to use tools and talk to each other? And, well, we do, but simply connecting tools together isn't enough. Our current standards, like Anthropic's Model Context Protocol or Google's Agent-to-Agent Protocol, are basically just communication protocols. They're fantastic at letting an agent talk to a tool, or letting Agent A talk to Agent B. But here's the catch. They don't natively support state mutation. They lack the built-in lifecycle and versioning support needed for an agent to safely modify its own internal components. To actually evolve, an AI needs to be able to mutate its own code safely, without destroying itself in the process.
Section 3. Layer 1. The substrate. The AI's DNA.
This brings us to the actual architecture of Autogenesis, starting with the Resource Substrate Protocol layer, or RSPL. Think of this layer as the cellular structure of the AI. Instead of a tangled mess of hard-coded text, RSPL strictly decouples 5 core elements: prompts, agents, tools, environment, and memory. It turns them into what the paper calls protocol-registered resources. And guys, this is huge. It means your system prompt or your Python execution tool isn't just a static block of text anymore. It's a version-controlled entity with an explicit state and a lifecycle. It acts as a standardized object that can be safely manipulated by the system.
And this is how it all brilliantly comes together. You have Layer 1, the RSPL substrate, acting as a structured database for all those core resources. These feed directly through a context manager that handles version lineage. This is absolutely the foundation that makes evolution possible. By externalizing these components, the AI can safely observe them, grab them, and swap them out without breaking the core reasoning engine. It sets the stage perfectly for the second layer of the protocol, which sits right alongside it.
Section 4. Layer 2. Self-evolution. Digital natural selection.
If Layer 1 is the DNA, Layer 2 is the mechanism of natural selection. It's a closed-loop evolutionary process based on control theory, and it strictly formalizes how the AI mutates through 5 atomic operations. Let's walk through it. Step 1. Reflect. The AI looks at an execution trace, say a failed math problem, and figures out exactly why it failed. Step 2. Select. It proposes a concrete fix, like rewriting a specific line in a Python tool. Step 3. Improve. It actually applies that mutation to generate a provisional candidate state. Step 4. Evaluate. It tests the mutated tool against a benchmark to see if it actually works better. And finally, Step 5. Commit. It locks in the change. The AI has officially evolved.
But what if the mutation is a total failure?
What if the AI accidentally makes itself dumber? Well, that's where version lineage comes into play. Every single evolutionary step in autogenesis is traceable and reversible. It functions exactly like a video game save point, or, if you're a developer, a git commit. If the evaluation phase shows that the mutated AI performs worse, the commit operator just rejects the change, and the agent instantly rolls back to the previous working version. It is literally evolution with a guaranteed safety net.
Section 5. Testing the evolving agent. Does it actually work?
The theory is incredibly elegant, for sure, but we want the hard evidence. So researchers put an Autogenesis-powered agent to the test across some of the absolute hardest benchmarks in AI, and the scale of improvement is just wild. When testing on the highly complex AMY 2024 math benchmark, allowing the agent to evolve both its prompt and its solution resulted in a staggering 71.38% improvement for weaker models. Because weaker models make more correctable mistakes, Autogenesis gives them this untapped potential to catch those errors, propose fixes, and basically bootstrap their way to a correct answer. The data really drives the point home here. When you compare a vanilla agent, one just taking a single static shot, against an agent using the combined evolve prompt plus solution strategy, the results are clear. Across the board, from GPQA to ME, the evolving agent absolutely dominates. Why? Because refining both the instructions and the solution covers completely complementary blind spots.
But math is one thing, right? What about messy, real-world tasks? Well, on the Gaia benchmark, which tests complex web browsing, file analysis, and long horizon planning, Autogenesis achieved state-of-the-art results. Most impressively, on the absolute hardest level 3 tasks, the system saw a 33.34% performance gain. This emphasizes that tool evolution provides the most leverage precisely when tasks are the most complex. Think about it. If the AI doesn't have the right tool to complete a multi-step workflow, it doesn't just fail. It pauses, uses its tool generator agent to write a brand new tool from scratch, registers it to its own DNA, and just keeps going. It's honestly mind-blowing.
We can literally see this continuous learning in action when we map out pass rates and runtime efficiency on LeetCode benchmarks. Over time, the gap between a standard vanilla agent and our evolving agent just widens and widens. As the evolving agent encounters more problems, it's not just passing more of them, it's actively optimizing its own runtime and memory efficiency. Its capabilities are continuously compounding. It's replacing suboptimal algorithms with highly efficient ones, learning and adapting completely on the fly.
Section 6. The new AI paradigm. Automated protocol engineering.
We've covered a lot of ground today, from brittle, monolithic agents all the way to safe mutations and hard benchmark data. So what's the ultimate takeaway for us here? It all boils down to this incredibly powerful quote from the paper. Autogenesis represents a shift from manual prompt engineering to automated protocol engineering. We are moving away from the era of humans writing endless text prompts and brittle Python scripts just to try and wrangle AI behavior. Instead, we are entering an era where we simply provide the AI with a standardized, safe protocol for self-repair, and we just let the system engineer itself.
And that leaves us with a truly fascinating and maybe slightly intimidating thought to end our explainer today. We've just seen how giving an AI a version-controlled, closed-loop system allows it to rewrite its own tools and instructions to achieve state-of-the-art performance. So if AI can now reliably engineer and evolve its own protocols without breaking, what will it build next? Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.